from our previous discussion, on polyphase decomposition, we saw that P of z must be equal to R of z times E of z, where R of z is the matrix of all the type 2 components for the synthesis filters and E of z are the analysis filters. And we saw that if P of z equals identity, right, then R of z is E inverse of z. Now, one of the questions that we have to ask is, are there necessary and sufficient conditions for perfect reconstruction property to be holding, and if so, what should be the nature of P of z for a simple 2 channel filter bank, and then we can extend this. So, this result was actually proved by P.P. Vaidyanathan, I think it is P.P. Vaidyanathan, and this appears in the Transactions on Acoustics, Speech and Signal Processing in 1987. So, I will just state the theorem. A necessary and sufficient condition for the perfect reconstruction property is P of z must take one of the following forms. That is, P of z is some scalar d times is the delay here 0 0 a delay, or P of z equals 0 z power minus k z power minus k minus 1 and 0. So, the proof is given in the paper that you can refer into, and I will leave this as an exercise. Now, this has some interesting consequences. That means I have a sort of a structure, I have a structure that I have to impose on P of z, right, and this should be of this form. And then if we were to look into how E of z and R of z have to be, are there any structures for E of z and R of z? Okay. So, let us start with the polyphase representation. Now, we have this E of z matrix in the form E naught of z, E 1 of z, and then this is E naught of z minus E 1 of z, right. We saw how this came about, because if you have H naught and H 1 as a column stack, that was the matrix 1 1 in the first row, 1 minus 1 in the second row times the components. Similarly, we have R of z to be of the form, if we impose this structure, then we look at R of z times E of z, that gives us this matrix 2 E naught of z, E1 of z, 0, 0 to E naught of z, E1 of z. Right, this is just rewriting, starting with the polyphase decomposition on the analysis bank and the synthesis bank, and then writing what R of z times E of z has to be. So this can be written in the form 2 times E naught of z, E1 of z times an identity matrix. Okay, so why do we need to do this algebra here? So, well, we want ideally R of z to be an identity matrix, which we may not get, right, or it is too restrictive. So, if I do not force it to be identity, let me have the QMF imposition on this structure, this quadrature mirror property. Therefore, I can synthesize my analysis bank and synthesis bank, and I can come up with a polyphase representation, and from this I can simplify what R of z times E of z has to be, and that can be expressed in terms of the polyphase components. If you closely observe this equation here, which is basically 2 times E naught of z, E1 of z times an identity matrix, we have a little more freedom in choice of E naught of z and E1 of z than just an identity matrix, right. So, one question that you may get is, a system is, one question that you might get into your mind is, how can we ensure that this is perfect reconstruction? That means this E naught times E1 should be some scalar times a delay, right. So, that is the intuition, and I think we start with that. Now, a system satisfies perfect reconstruction property if and only if E naught of z times E1 of z is a pure delay. So, if H naught of z is constrained to be a finite impulse response filter, it is possible if and only if E naught of z and E1 of z are pure delays. Well, that is what it is. I want E naught times z, E naught of z times E1 of z to be a pure delay. So, if I constrain H naught to be FIR, right. So, I mean, if it is not FIR, then I can think that I could cancel out somehow, right. E naught can have a denominator polynomial, and that denominator polynomial can be somehow factored in to one of the factors in E1 of z in the numerator. So, that is the reason why we are forcing it to be FIR. If it is FIR, then the components E naught of z and E1 of z have to be individually delays, right. So, therefore, this implies that H naught of z must be of the form H naught of z equals some C naught z power minus 2 times n naught plus C1 times z power minus of 2n1 plus 1. where n1 and n2 are n0 and n1 are just some integers, right. So, we have given the broad form here, it can be even or it can be odd. Now, if we need a FIR, we may have to give up on the condition h1 of z is h naught of minus z. Our filter banks allow us to do that, right. I mean, it is ideally easy for us to have one base filter h naught of z, from which we can get h1 of z and from which we can synthesize other filters. But if we did not want to have a quadrature mirror property to get the high pass filter, and I want to restrict it still to be FIR for the base filter, then it is difficult to get possibly an FIR filter which satisfies this property, right. I mean, you can plug in a minus z here and you will see what the effect is. Now, the idea in general is as follows. For a general perfect reconstruction, we let R of z to be some d z power minus k E of z. We will let it in this form. So, you may wonder why this form. I mean, that means E R of z times E dagger of so E is basically E inverse in some sense. Can we think about having such self inverses in polynomials? If E of z is minimum phase, a minimum phase filter is one in which the poles and zeros are inside the unit circle. So, if it is minimum phase, then R of z, hence the synthesis filters f k of z will be IIR but stable. Right, because if you just invert it, the zeros will become the poles and the poles will be 0. So, therefore, stability is ensured. The second point is, if somehow determinant of E of z lands as a delay, we can hopefully construct FIR perfect reconstruction quadrature mirror filter banks. So, basically we are looking at a family of lossless matrices that can give us perfect reconstruction. So, determinant of E of z equals some delay would certainly imply that we have a family of lossless matrices. This is, however, not a necessary condition for perfect reconstruction. Okay. So, the idea is very simple. So, R of z times E of z is P of z, and if we let P of z is some z power minus n naught, some delay, R of z is this delay with a gain with some E inverse, and the E inverse is 1 over determinant of E of z times adjoint, and if the adjoint somehow works out to be of the form of E of z itself, then you know we are home for good, right. Such matrices which have this property are good. Now let us consider an example for the design of such synthesis filters. Small thing to note, this has to be an inverse here before we wrap up with this slide, just a detail, because R times E of z must be basically D times a delay. So therefore this has to be E inverse. Suppose H of z is 1 plus z power minus 1, 1 minus z power minus 1, 1 minus z power minus 1, 1 plus z power minus 1 as shown. Now H of z times H bar of z should be some C times identity for lossless conditions. If you expand H inverse of z, this is routine algebra, you could do this. It is 1 by 4, 1 plus z, 1 minus z, 1 minus z, and 1 plus z. Now suppose R of z is C times z power minus k times some E inverse of z, right, where k is some delay that we can choose, so that the system is also causal, right. You want to ensure the system is causal for certain reasons. The gain is in your control. So let us see what happens when E of z is basically H of z, right, that is E of z is H of z. Now we plug in k equals 1. Let me call this equation say 1. In this equation I plug in k equals 1. I can choose whichever delay I want to choose, it is an art, right. Let me plug in k equals 1 and I choose a factor C appropriately, right. Then I can have R of z is basically you multiply H of z by this delay, right. So basically it is z power minus 1 times this, z power minus 1 times this term, so on and so forth, right. So I do this, I get 1 plus z power minus 1, z power minus 1 minus 1, z power minus 1 minus 1, 1 plus z power minus 1. Now I know the structure of E of z, right. I know the structure of E of z, which is basically H of z, right. So just recall from your previous worksheet here, E of z is H of z, I am rewriting it again. So my H naught of z, the first polyphase component, is E naught naught z square plus z power minus 1 E naught 1 z square, and and here I think one thing that you have to note is C is chosen to be 4. I have just taken, I just ignored it, but I think it is implied that I take C equals 4, K equals 1 and C equals 4, I get this. So you do the math, this comes out to be 1 plus z power minus 2 plus delay times 1 minus z power minus 2. To simplify this is 1 plus z power minus 1 plus z power minus 2 minus z power minus 3. Okay. Similarly, we have h1 of z, which is E10 z square plus z power minus 1 E11 of z square, which is 1 minus z power minus 2 plus z power minus 1 times 1 plus z power minus 2, which is equal to 1 plus z power minus 1 minus z power minus 2 plus z power minus 3. And analysis filters H0, H1 are indeed FIR. Now we can do this for the synthesis bank. So we get f naught of z is z power minus 1 r naught naught z square plus r 10 z square, and f1 of z is z power minus 1 r naught 1 z square plus r11 z square, and you plug in, you get f naught of z is z power minus 1 times 1 plus z power minus 2 plus z power minus 2 minus 1, which is minus 1 plus z power minus 1 plus z power minus 2 plus z power minus 3, and f1 of z is, you do the math, you will land up with this equation, and we still have synthesis filters to be FIR. Okay, and this is still good for alias cancellation, because f naught of z is h1 of minus z and f1 of z is minus h naught of minus z, and then this is still good for alias cancellation. So it is not necessarily true that you have to start with quadrature mirror property. You can relax that if you want to, have your choice of f naught and f1 based upon what you would choose for your h naught and h1, right. You have a choice that you could make for your high pass filter h1, but ideally it is preferred if we can get a one base filter and from which we can synthesize the rest of the filters. Else, if we want to keep the design a little more flexible, then we have to basically have two different filters in the analysis bank, and we can have similar filters in the synthesis bank. Okay. And then of course you could analyze the system for phase distortion, amplitude distortion and other artifacts. Okay. With this we are done with perfect reconstruction property. We looked into the 2 channel filter bank, we looked at the generalization to m channel filter banks, we saw how polyphase decomposition is very useful for this purpose, and we also have ways in which we can construct FIR filters that satisfy perfect reconstruction property. okay, and this design is going to be very useful when you have to design filter banks and that work with oversample or systems which have decimators and expanders along with filters. Okay. So, we will discuss in the next class special filters and some of the properties, and these filters would be very useful for designing these filter banks. So, there will be additional constraints. Okay. We can end this lecture.